Okay, so let's look at the question now on how you can calculate the reading and uncertainty of a particular physical quantity. So look at this question. A ball made of a metal has a mass given as m equals 53 plus or minus 2 grams. The radius of the ball is, this is the diameter of the ball is measured as d equals 3.5 plus or minus 0.1 centimeters. Calculate 1. The density of the ball in kilograms per meter cube. Then 2. Calculate the absolute uncertainty of the density. Alright, so you are given a ball, the mass and the diameter of the ball were measured, and the values of the mass and the diameter have been given above. So what we want to do now is to calculate the density of the ball. And you are supposed to calculate the density in standard unit, which is kilograms per meter cube. So you know that the unit for mass and diameter, they were given in centimeters. So if you are solving this problem, you need to calculate the reading of density in standard unit, which is kilograms per meter cube. We know that density, the symbol for density is rho, is given as mass per unit volume. So the density here will be the mass per unit volume. But if you look at this equation there, you will see that the density is defined in terms of volume. Volume is calculated from diameter. So volume is also a calculated reading. But the calculated reading you want to find is density. So you have density defined in terms of another calculated reading, which is volume. You have two ways to solve this problem. The first way is for you to first calculate the volume from the diameter. And when you do that, you also calculate the absolute uncertainty of volume before you now use what you have gotten for volume to determine the reading for density. Instead of doing it like that, because volume is calculated from diameter, why not express volume in terms of what? Of diameter. How do we do that? The volume of a sphere is given as 4/3 power cube. The radius in terms of diameter is d/2. So if I substitute for this, I'm going to have volume to be given as 4/3 pi d/2 all cube. So the volume there will be given as 4/3 pi d cube over 8. This will give you 2 here. So the volume becomes pi d cube over 6. So density can now be given as mass over volume. And the volume is given as pi d cube over 6. So the density becomes what? 6m over pi d cube. So here, I have now expressed density in terms of mass and diameter, which are the two given readings. Which means they are the two readings that were measured. Alright? So from there, we can calculate the density. So the density, this becomes 6m. Mass is 53. But remember that the mass here is given in grams, but we're supposed to express it in kilograms. We're supposed to express it in standard units. So we have 53 times 10 raised to the power minus 3, converting from grams to kilograms. 6m over pi. The diameter is given as 3.5 centimeters. You convert it to meters. Converting from centi, the prefix for centi is 10 raised to the power minus 2 meter cube. So from here, you can use your calculator to now find what? You can use your calculator to now determine density. And I have my own calculator here. So I have this. So you are going to have 6 times 53 exponential minus 3 divided by pi times, you put that in the bracket, 3.5 exponential minus 2, then this is cube, all raised to the power 3. So if you do that, the density becomes 2,361 kilograms per meter cube. This is the density in standard unit. Then we can now calculate the absolute uncertainty. Remember that density was calculated from what? From division and multiplication. And if a reading is calculated from division and multiplication, how do you calculate the uncertainty of that reading? You use the method of addition of fractional uncertainties, which means the fractional uncertainty in density will be equal to the additions or the fractional uncertainty of the constant readings of density. That becomes the fractional uncertainty in mass plus 3 times the fractional uncertainty of diameter. We have explained before that pi is a number, it doesn't have uncertainty. D, when a reading is raised to a power, you multiply the fractional uncertainty of that reading by that power. So I can now say the fractional uncertainty in diameter, which is uncertainty in diameter or reading of diameter, 2361, will be equal to the addition of the fractional uncertainty of mass, which uncertainty in mass, that is 2/53. Remember that uncertainty is a number, it doesn't have unit. So if you are calculating for the fractional uncertainty, fractional uncertainty is a number, it doesn't have unit. Because the uncertainty and the reading, both of them have the same unit. So unit will cancel out. What does this mean? When you are calculating for the fractional uncertainty, you don't need to convert it to standard unit. Because both of them have the same unit. So unit will cancel out. Plus 3 times the fractional uncertainty of diameter, that is 0.1 over 3.5. So if you do this with your calculator, the fractional uncertainty of density becomes, so you have this 2 over 53 plus 0.3 over 3.5, and everything here will give you 0.1235, so that the absolute uncertainty of density will now be the reading of density, which is 2361 multiplied by the absolute multiplied by the fractional uncertainty, 0.1235. So when you do that, times 2361. So this will give you 291.5 kilograms per meter cube. Because everything here does not have unit. But this has the unit of density, which is this, which is kilograms per meter cube. So by the time you cross multiply, the unit of the absolute uncertainty of density will still be the same as the unit of density. So the density there will therefore become what? The density we can therefore be given as 2361 plus or minus 292 kilograms per meter cube. So if you are required to express this to the appropriate number of significant figures, you have to express this reading to the same number of significant figures as any of its constant reading with the lowest significant figures, which is 2 significant figures. So density will now become 2,400 plus or minus 290 or 292. 290 kilograms per meter cube. If the reading does not have decimal place, then the sanity should not have decimal place. But the reading should be presented to the same number of significant figures as any of its constant reading with the lowest number of significant figures. So that is that. You can as well, you could have calculated for the uncertainty of density by adding the percentage of certainty, but it will be longer because that will imply that you first find the percentage of certainty of each of these readings before you then add the percentage of certainties of the calculated reading. Then from the percentage of certainty, you can now use that to now calculate the absolute of certainty, looking at what we have done previously. So when you are finding absolute of certainty using the method of addition of fractional certainties or addition of percentage of certainty, both of them will give you the same thing. So the one you should use per time, according to my advice, depends on the way the question is posed. That is what should determine the approach that you should use, as we see in the next question. Alright, before we go to the next question, what are the major highlights from these questions? The first highlight from this question is that if a reading is expressed in terms of another calculated reading, instead of you first finding the calculated reading and the certainty of the calculated reading, then using that to find using that to determine another calculated reading. It is easier for you to just express that calculated reading in terms of the given reading. As you can see here, we just express volume in terms of what? Of diameter. Then density, so that we can now express density in terms of diameter rather than expressing density in terms of volume. That is number one. Then number two, when you are calculating your values in standard units, it is the reading that you should convert to the standard unit. You don't need to do that for the fractional uncertainties, because the fractional uncertainty is a number without unit. So that the unit of the absolute uncertainty will just be the same as the unit of your reading. Okay. Let's look at another question. Okay, so let's look at this question now. The force exerted on a circular surface is given as F equals 20 plus or minus 5% newtons. The diameter of the surface, is given as D equals 5.0 plus or minus 10%. Calculate 1. The pressure exerted on the surface. Then II, the absolute uncertainty of the pressure. Okay, so we do that. So the pressure, then our pressure is given as force per unit what? Area. Force exerted per unit area. But area is a calculated reading. According to what I've expressed previously, it's better you just express area in terms of what? Diameter, which is a given reading. So area is given as pi r squared, area of a circle. And radius is given as diameter over 2. So area becomes pi d over 2 all squared. This will give you pi d squared over 4 if you expand this. So I can substitute for this as pressure becomes force over pi d squared over 4. So pressure becomes 4F over pi d squared. So I can calculate the pressure now to be 4 times 20. This is in centimeters. 4 times 20 is given in newtons over pi. The diameter is given as 5.0 centimeters. And we are calculating the pressure in standard unit in pascals. Pascals, remember, is kilograms per meter per second squared, which is standard unit. So that means that force should be in newtons, the diameter should be in meters. So that becomes pi 5.0 centimeters. Convert that one to meters. You multiply with 10 raised to the power minus 2 all squared. So I can now use my calculator to determine pressure. You too, you can do it. Use your calculator. If you have a scientific calculator, it will save you a good amount of time. So you have this, you have something like this, you press this, so you have 4 times 20. You come here, your scientific calculator, you put this, that's pi, open the bracket, 5.0 exponential minus 2, you close your bracket, you square that. So this will give you 10,190 pascals. Okay? Then from here, since you were given the percentage of certainty of each of the readings, it will be easier for you to just calculate for it will be easier for you to find the absolute of certainty by first calculating the percentage of certainties. Now we have said that if a reading is obtained from multiplication and division, the percentage of certainty of your calculated reading will be equal to the additions of the percentage of certainties of its constituent readings. So here, the percentage of certainty of pressure will be equal to the percentage of certainty of force. You don't need to put times 4 there because this 4 is a number. It's not a physical quantity. Plus pi is a number, it's not a physical quantity. Plus 2 times the percentage of certainty of diameter. We have said that if a reading is raised to a power, you multiply the percentage of certainty of that reading by that power. So the percentage of certainty of pressure becomes the percentage of certainty of force, which is 5% plus 2 times 10%. This will give you 20 plus 5, 25%. So this basically means that the percentage of certainty of pressure is 25%. So the absolute of certainty of pressure will just be 25% of the reading of pressure, which is 10,190. This is 0.25 times that. So you continue with your calculator there. And this will just give you 2,546. So that the unit of the absolute of certainty of pressure will be the same as the unit of pressure. So you can now write your pressure to be 10,190 plus or minus 2,546 pascals. And if you write this to the appropriate number of signal figures, you are going to have pressure becomes 10,000 plus or minus 2,500 pascals. Okay? All right. So those 2 examples are very, very important for you to be able to calculate the value of a reading and also find the certainty of that reading. So the procedure we have used there is the procedure which is the same procedure here. if your reading is expressed in terms of another calculated reading, just express the calculated reading in terms of the given reading, so that you can express your calculated reading in terms of the given reading, instead of you first calculating for this calculated reading and finding the uncertainty of that reading. It take you a longer time. Just express the calculated reading in terms of the given reading. And when you are calculating, because the uncertainty is expressed in percentage form here, it will be easier for you to just calculate the percent uncertainty using the additions of the percent uncertainty of the constant readings. Because if your reading is calculated from multiplication, from division and multiplication, the percentage uncertainty of that reading will be equal to the addition of the percentage uncertainties of its constituent readings. That will give you 25%. So the absolute uncertainty will now be 25% of that reading. And that will give you this. Then you can now go ahead to express your answer using the appropriate number of significant figures. Alright. So having said that, let us move on quickly. Let us move on quickly. So having said that, let us move on quickly to precision and accuracy of readings. Let us move on quickly to precision and accuracy of readings. What does it mean when we say a reading is precise? A reading is precise. A reading is precise if the range of value is narrow. If the range of value is narrow. So a reading is precise if the range of value is narrow. It has a narrow range, which means that the difference between the highest value and the lowest value is very, very small. So when you are talking about the precision of a reading, remember that according to what I've just said now, a set of values, okay, precision and accuracy of readings. So what do we mean by precision of a reading? A set of value, precision is the degree of narrowness of a range of values. When we say a set of values are precise, it means that the range is narrow, meaning that the difference between the highest value and the lowest value is very, very small. Okay? For example, if I take a set of readings for the acceleration of free fall, which is g, and I have this set of readings for the acceleration of free fall, you have g in meters per second square, g1, g2, g3, g4. The first one here is 8.83, 8.81, 8.82, 8.80. If you look at these sets of values, the sets of values are precise because their range is narrow. But if I have 10.01, 9.75, 9.81, 10.04, this set of values are not precise because their range is farther apart, which is different between 10.04 and 9.75. Then when we talk about accuracy, accuracy is the degree to which the mean value of a set of readings is close to the true reading. Is the degree to which the mean value of a set of readings is close to the true reading. Which means that in accuracy, I'm looking at how close is the mean value of the set of readings to the true reading. So in accuracy, you have to know the true reading. So for example, if I look at these two sets of values, which of them is accurate? You see that the set of values for one is not, it is not accurate, but it's precise. Because the mean value of this set of readings is not close to 9.8, which is the value taken to be the acceleration of free fall on the surface of the earth, or acceleration due to gravity. But this value, the second set of values, the value is accurate. But if you take the mean value of this set of readings, it will be close to 9.8. Therefore, the set of values in 2, it is accurate. But the set of values in 1, it is precise. So I can describe the set of values for 1 as precise but not accurate. The second value as accurate but not precise. So if I bring in another set of values like 9.81, 9.80, 9.79, 9.79, 9.82. This set of values are precise and they are also what? Accurate. I also bring in another one, 8.83, 7.29, 9.43, 9.87. This set of values are not precise and the set of values are also not accurate. What that means is that if you take the mean values of this set of readings, it will be far from the values of the acceleration of free fall, and the range of the value is wide. That's when between 7.29 and 9.87 meters per second squared. So that's how we, and in the experiment, it is you have a lot of emphasis to the precision of your readings. Your readings should be well precise. That's very, very important, because accuracy of your readings will not depend on the set of instruments that you are using to determine the values. And that will take us to the next set of discussion, which is systematic and random error. So we look at systematic and random errors. We look at the next set of values. The next set of discussion is systematic and random error. When we talk about systematic error, what does it mean? And when we talk about random error, what does it mean? So the next thing we'll be discussing now is systematic and random errors. Systematic errors and random errors. When you are performing an experiment, you have two sorts of errors. The errors can either be coming from the skill set or the experimenter, which means the error depends on the person that is taking the readings. The precaution is able to follow. The precaution is safeguarding its methodology.